Hi friend, you are welcome back to my channel, and in today's class we shall be learning about another important topic in physics, which is simple machine. So without wasting your time guys, we'll be getting started now. First thing first, for simple machine there is something called mechanical advantage, abbreviated as MA, that you need to know about. It's simply the ratio of two forces. We are going to be what? Dividing one force by another. So from the formula that we have here, we said that mechanical advantage is equals to what? Load over effort. Load over effort. Each of these are a form of force. Okay? Now L here is the load, or it's also called the output force. E here is the effort, and it's also called the input force. So when you do a ratio of the load and effort, or you say the output force to the input force, what you will get is called the mechanical advantage of that machine. Next other thing we must know before we get started is what is called velocity ratio, abbreviated as VR. VR. Now this is simply a ratio of the distance covered by the effort over the distance covered by the load. Now there are differences in their representation. I gave this as capital L over capital A. While for velocity ratio, it's given as small letter e over small letter L. Okay? Where E is the distance moved by the effort, L is the distance moved by the load. So take note of these two key formulas before we get started. And also there's something called efficiency. Efficiency, abbreviated as E or EF. Now, what are the formulas we can use to get the efficiency of a machine, to tell how efficient that very machine is? The first formula here is MA over VR times 100%. Like we know, MA here stands for what? Mechanical advantage over VR, where VR stands for what? Velocity ratio. Whatever you get times it with 100, that will give you the efficiency of that machine. Another formula we can make use of is this, and this is simply an expanded version of this guy here. Okay, so when you simplify the formula using this and this, you will get this. And what do we have there? Efficiency is equals to the load times the distance moved by the load over the effort times the distance moved by the effort. So we are having load times distance moved by load over effort times distance moved by effort. Everything times what? 100%. And this will also give us the efficiency. Now if you observe clearly, we are having a form of force times distance. I remember whenever force is times in distance, that quantity is called what? Work done. So this is will give us the work done by the load over the work done by the effort. Remember, work done by the load is also the output work. Okay? While work done by the effort will now be the what? Input work. So the output work over the input work times 100% will also tell us the efficiency of that machine. Now sometimes you might not be giving the output work directly, and like I said, the output work is the work done by the what? The load. Now you might not be giving the output force directly. Sometimes you might be giving the work done by friction, because in most realistic or real case machines, friction is usually present, and some of the work will have to be done to overcome friction. So the remainder of it will now be used to what? Move the machine. Okay? So sometimes you might be giving the work that was done against friction, and you might be giving the input work, that is the work done by effort. So how do you now use the source to get the efficiency? The formula is work done by input force is minus work done by the frictional force over work done by input force. Everything times 100 will give you efficiency. So this is another formula you can use to get your efficiency. So quickly take a look at all of this, right from mechanical advantage to velocity ratio and then to efficiency. Now guys, now we know this, we will be looking at what we have here. They say that in the presence of friction, the value of Na, and what is Na? Na is telling us what? The mechanical advantage. The value of Na reduces. So as the friction increases, or as the frictional force increases, the value of Na tends to become smaller, but that of VR remains unchanged. So whether there is friction or there is no friction, the value for VR for a particular machine is constant. Is that clear? Now the next point is that in the absence, and this is typical in an ideal situation where everything is perfect. In the absence of friction, okay, the value of MA and that of VRO will be what? The same. So for the first scenario where friction is present, MA tends to be less than VRO. For the second scenario where there is no friction, MA tends to be what? Equals to VRO. I hope that is clear, guys. So about now, we're looking at what I call the types of simple machine. We've known the formulas we need to have, the introductory formulas we must have at the back of our mind. So about now, let's see what are the common simple machines we can find in physics. You have one, lever. Number two, we have pulley. Number three, we have the inclined plane. Number four, we have the wedge. Number five, we have the screw jack. Number six, we have the wheel and axle. And lastly, we have the gear wheels. So these are the basic example or types of simple machine we must know. And there are some key things to be taken note of under each of them. And that is what we'll be looking at now. So that will bring us to a discourse on each of these types of simple machine. So let's have that now. Alright guys, so about now, we shall be looking at each of the simple machines and what we need to know other them. So let's look at the first. We have lever, okay? Now looking at it very closely, this is a typical diagram of how a simple form of a lever looks like. Now you have the effort force applied at this end, then you have the load force applied at this end, then this thing at the center, which is called the pivot, is usually the axis about which this lever rotates, okay? It is called a fulcrum. This pivot is also called a fulcrum, okay? F for short. Now, the distance from this point of application of the load force to the fulcrum is small letter L, while the distance of the application of the effort from this fulcrum is the E, small letter E that you are seeing here. So you have effort, load, fulcrum, small e and small l. So this is the typical diagram of how a lever looks like. Now there are three classes of lever. You have the first order lever, you have the second order lever, and lastly you have the third order lever. Now why are they distinct from each other? Why is some called first order, others called second order, and others called third order? Now this is the distinction. For your first order lever, in this one, the F here is talking about the fulcrum. The fulcrum is between the load and the effort. So when you analyze the structure of the simple machine that is a lever, and you discover that the fulcrum is in between the load and the effort, it shows that that lever is a first order lever. But if the load is now what is between effort and fulcrum, it's a second order lever. But if it's the effort that is between L and F, it's called a third class order. What do I mean by this? Now, how does this represent here? You will have something like E here, something like F here, fulcrum will be here, the pivot will be here, then the L will now be here. Okay, this thing you are seeing will now be in the middle. So that one is called the second order lever. While for third order lever, they said E will be in between L and F. So while L will be here, the fulcrum will be here, E, the force called effort, will now be in the middle. That one is called a third order lever. Now they have examples, and some of these examples are usually tested for in common O-level exams like JAM, system, and even WAEC. So let's see some of the common examples of first order lever. You have scissors, you have crowbars, you have claw hammer, you have plier, and then you have pinchers. So just take note of this for an exam condition. Now, next for your second order lever, I've already said that the load is in between E and F, that is effort and the fulcrum. Now, example of such, you have wheelbarrow and nutcrackers. Now, lastly, for your third order lever, in this case, it is the effort that is between the load and the fulcrum. Now, example of such, you have forceps, tongue, and the forearm. The forearm, okay, is an example of a third class or a third order lever. Now, there's an abbreviation, you don't need to cram. Oh, in which one is the load in between effort and the fulcrum? In which one is the effort between load and the fulcrum? You don't need to cram. I just pick out the middle. What is in the middle? What is in the middle for the three type of lever? You have FLE, so you say flee. Now for your first, or this one is what of occur first. For your first order lever, fulcrum is in the middle. For your second order lever, load is in the middle. For your third order lever, effort is in the middle. So I hope this helps you. You can look through it. So let's go to the next type of simple machine, which are the pulleys. Now each of these is like a round disc. Okay, one round disc, two round disc, three round disc. Okay, there's another one here and there's another one here. So this arrangement is called the pulley system. It's called the pulley system, and it's used for lifting heavy loads. Okay, that you won't be able to lift ordinarily with your bare hands. This is the load I'm talking about. Okay, this quadrilateral structure is the load. Okay, now what is it being used for? It's used for lifting heavy load. You will just apply a little force here called the effort, because that is the effort. That's the force you are rendering. It's called your effort force. Why the load will what? Move up because of this arrangement of pulleys. It will go to what? Lift it up no matter the size. I hope that is clear. Now, there is something you need to know. Sometimes you may be asked to calculate the velocity ratio when you are given any type of a pulley system. How do you now get the velocity ratio of a pulley system? The formula is the velocity ratio is equals to the total number of pulleys. Now we said this is one pulley, this is second pulley, this is another pulley, that's 3, this is 4, and lastly this is what? 5 pulleys. So in total for this very type of pulley arrangement, we have 5 pulleys. So our velocity ratio is equals to what? 5. Now if we know the velocity ratio now as 5, perhaps they have told us what the efficiency of the machine is. We can look for the mechanical advantage, is it not? Using the formula for efficiency. So that's how the calculations are being generated. It's not hard, it's very easy. Now, going straight to the next type of simple machine, which is called inclined plane. If you look at it, the surface of this machine or this structure is inclined at an angle. So that's why the whole machine system is called an inclined plane. Now there's an important formula you need to know under this inclined plane. It is called the velocity ratio of an inclined plane. And the velocity ratio of an inclined plane is given as this. The velocity ratio of an inclined plane is equal to 1 over sine theta. Theta is the angle of inclination. So if it was given as 30, it will be 1 over sine 30. If it was given as 60, it will be 1 over sine 60. If it was given as 45 or whatever they give, it will be 1 over sine of that given angle. This is an important formula for the velocity ratio of an inclined plane. Do well to take note of it. And next, you have the wedge. Now, you've seen something like an axe, a pickaxe, and the rest. That is used for what? Let's say splitting substances, let's say wood and others. Now, this is how it is. You have these two slanty sides, and this is the sharp edge that is used to what? Split, say, a wood, right? That is to split a wood. Now, this is how it looks like. Now, there is an important formula under a wedge that you need to know. It's the mechanical advantage of a wedge. The formula is the mechanical advantage of a wedge is equal to the slant height. You are seeing it symbolized by this. So whatever is the length of this part, you will put it up here. Over the thickness, this is it. Whatever is the value they put here, you will put it under. So if you do your division, whatever you get will stand for your what? Mechanical advantage. Okay? That is how it works. Now we still have things like screw jack, we still have others like wheel and axle and the rest. So now we've known the important formula and the important point we need to know for this type of simple machine. I'll be giving you guys the rest of them. So let's have those ones now. Alright guys, so lastly we shall be looking in details at the screw jack, then we'll be looking at wheel and axle, and lastly we'll be talking about gear wheels. So let's get started. This is the typical diagram of a screw jack, okay? Now these are the screws, these serrated structures. Then this is the jack or the handle that is used to what? Turn it or press the jack. Now this is how a screw jack looks. Now observe something. From this point to the end of the handle is called arrow. Okay? While the distance between these screws, the distance between two consecutive screws is called a pitch. I repeat, the distance between two consecutive screws is called a pitch. abbreviated as P. So if by chance you want to get the velocity ratio of a screw jack, this is the formula you use. It is 2 pi r over P, where P is the what? Pitch, and r is the what? The radius, that is from here to here. Now, like I said, once we are able to calculate the velocity ratio, if by chance we are given the efficiency of this screw jack, we can get the mechanical advantage using the formula for what? Efficiency. That's how it works. Next, we'll be talking about the wheel and axle. Okay, this is a common structure in boats. Okay, usually for dropping anchors and the rest. Now, this is how it simply look like. Now, you have this larger wheel, and then you have this cylindrical structure attached. The larger wheel is the wheel, as the name implies, while the cylindrical structure attached is called the axle. So it's a wheel and axle. A wheel and an axle. Is that clear? Good. Now, there's something we need to know. Sometimes you might need to find the velocity ratio of a wheel and axle. How do you get that? Now, if you look at this wheel, there's a center. Though this structure in physical won't allow you to see the center. So from that center to this point, on the circumference of the wheel, is the arrow, the big arrow you are seeing, and that's what we here. Now, on this cylindrical structure, let's say at this end, there's a center also here. Now, from here to this point on the circumference is the small arrow you are seeing here. So, if we know the radius of the wheel and the radius of the axle, we can get our velocity ratio. So, this is the formula. Now, next, we have lastly the gear wheels. Gear wheels. Now, if you see, these guys have a serrated structure too, so this is the gear wheels. Okay? Now, sometimes you may also need to find the velocity ratio of the gear wheels. The formula to use is capital N over small n. Now, when capital N stands in full for the number of teeth in the driven wheel. Mind you, driven over driving. I repeat, the driven wheel over the driving wheel. This is it. The capital N stands for the number of teeth in the driven wheel. These things you are seeing, they are counted, okay? So if you have 38 of them in the larger one, it will be 38. If you have 24 here, it will be over 24. Is that clear? Now, sometimes they can also say number of teeth for the big end, number of teeth in the larger wheel over number of teeth in the smaller wheel. So any of them will work, provided you're able to get your velocity ratio. So guys, these are some of the important formulas you need to know under each of the simple machine. I hope you find this video lecture on simple machine helpful. Thanks for watching. I will see you guys in my next video.